Okay, well, for your listening pleasure, back with the third Power podcast. We're in this period of the class where I'm realizing there's only a month to go and there's quite a bit of material. Though we have covered a lot, and sometimes I do a slide called We Are the Champions, how much material we've really gotten through, because it kind of sneaks up on you. By this point in the semester, there's a lot of stuff covered, and really not that much out there that's kind of uniquely space oriented. So I've been talking about power on the podcast, talking about management in class, in part because power. I mean, management has a lot of stories. Power is a lot of facts. So maybe it fits better the podcast type of presentation. The last slide we did was slide 8 on why my ex-manager and many other people who are systems engineer in the space business focus their first emphasis on power. And because they realize that everything else is going to follow the power, because the power is going to determine your aperture, and your aperture is going to determine how big the satellite is going to be, and deployables and batteries, and pretty much the single biggest element of the mass budget of a satellite is going to be the power system. So it's a pretty big deal, and especially if you're going to go away from the Earth a little bit, say toward Mars, there's always the idea, well, why don't we just use a radioisotope thermoelectric generator that just makes heat, and use a reverse thermocouple to turn that heat into electricity. And of course, we do that for deep space missions, interplanetary missions, but they are very, very difficult to get approved, and there's a very limited number of them in the world, and it's just if there's no other choice, and you can make the case that there's no other choice, you can do it. NASA's currently on a kind of program to show that even going to Saturn, which has 10 times further from the sun than Earth, and therefore 1% of the radiative flux, could be done with solar panels. So you've got to have a fairly difficult problem. In the seminar on Friday, Creer was talking about how much better it is if you can run a rover on thermoelectric generators, which I guess they did back then, but that was back then, and this is now, and it is a lot harder. People, maybe not justifiably, but they worry that if there were a launch mishap and the thing would come crashing to Earth, that the plutonium could be released. I mean, obviously that's been thought about quite a bit before they ever launched the first one. So, and then there's always the exceptionalism that we think that if we didn't launch them, there wouldn't be any. But of course, we're not the only people in the world putting things into space. If you go to, various places that you might want to go to, it could be very difficult to make electric power with solar panels. We just live in a happy accident on Earth in so many ways. And one of them is that we have enough, we have 1,300 watts per square meter of flux in orbit, which is, a lot. I mean, a meter isn't very big. I mean, if you think of a beach umbrella as a couple of meters. So speaking of beach umbrellas, slide 9, what I'm really trying to say in this slide, which is maybe a little bit of, elementary school arithmetic, is that any little innovation on the digital side, all of a sudden we want to send 10 times more bits down to Earth, right? Or, we want to do something like drilling into the surface, which takes a lot of power. It's very easy to come up with reasons why 1 or 2 watt power budget or a 10 watt power budget is not sufficient. You want to do a transmitter at a higher frequency, a shorter wavelength, X-band, 10 gigahertz type thing. And the transmitter efficiencies there are 5 to 10%. You need a couple of watts. Therefore, you're going to need, 20 to 50 watts of DC power into that transmitter to get those few watts out of it. That may be very convenient for your bit budget, but it's not very convenient for your, for your power budget. So, there's a lot of demands for power. There's a lot of people out there saying, oh, I need more power. The trouble is the supply of power is kind of very linear. If you want 10 times more power, which is very easy to decide on the satellite, just a change in the frequency will change by a factor of 10 the amount of power that you need in the transmitter, and 10 times the data rate could just be a 10 times better camera or a 2 times better camera in terms of resolution, in terms of number of pixels, but more depth on more bits in each color, and that can be very useful for discerning temperature, for discerning different minerals in the soil. We have multispectral cameras that are sensitive to hundreds or thousands of different spectral bands, or you can think of them as kind of bins, breaking up the black body radiation into 1,000 bins. That gives you a lot of data when you run a camera like that, because you need a number for every one of those bins, for every one of your pixels. So those kinds of things put a tremendous demand on power, not to mention, like on the lunar rover, it needs heaters, because when you're not in the sun on the moon, it gets very cold and you're going to freeze down your batteries and everything else. How are you going to charge those batteries when you are in the sun? With gigantic solar panels. So it's easy to think of missions that need a lot of power, and it's hard to think of ways to make a lot of power, only because it's linear in area. And so, and like we went through before, solar panel efficiency coupled with all the other inefficiencies, your overall power system, even though there is 1,000 watts per meter out there, a meter is going to give you 20 watts of steady state, reliable power when you take all the other factors into account. If you have a big satellite, you can point the solar panels at the sun and you're in geo so that you're only in the shade 20 minutes a day. Sure, that number is going to get bigger. But talking about low Earth orbit, talking about sitting on the surface of the moon, a lot of real world situations, that 2 or 3% rule of thumb is a pretty good rule of thumb. So, your real weapon as a power engineer is disciplining the payload down to lower power, and they don't like it. But also many times they are people who've been working on other kinds of systems that either are much bigger satellites with much more power, or they're, or they're satellites that, or they've been working on non-satellite projects where you have the wall plug. The wall plug is pretty evil. Okay, so I have a little slide on deployables, which I think we've talked about in the past. The idea of printing solar panels in space is a totally fascinating thing to me, and this covers slide 10, 11, 12. We did this as a design exercise in class many years ago. If you can make your deployable big enough, you really don't care how efficient the solar panel is, and by printing the solar panels onto aluminized mylar and just rolling them out, and assuming you have some kind of like measuring tape type of mechanism to keep them stiff. I mean, there are problems with this in that how do you point it at the sun, and maybe you have to spin it in order to keep them, in order to keep them, stretched out as I'm showing them in the picture. But on the other hand, compared to what we do now, we would have considered that impossible, to build these gigantic panels that are very fragile. Germanium, it's pretty, pretty rigid material, very easy to crack, and then covering it with glass, and very thin glass, to keep the mass down and to keep the absorption down. And, then to launch that thing with all the launch load vibrations. And then you've got to put all that mass in space, of the glass, of the panel itself, and of the substrate underneath it, usually some sort of carbon composite, what I call the paddle. Even if your solar panel efficiency is fairly low, as I'm showing on slide 14, you can make, pretty much 10,000 watts of power with a reasonable sized, with a satellite that's a cubic meter when you start off. And why we don't work harder on this, I really don't know, to tell you the truth. It seems to me like that would be the future, to just roll out aperture instead of building the aperture on the ground and then trying to deploy it in space. I kind of went from that, and this is not really quite on the power axis, let's say, to a long discussion here of deployables. Because usually when we have a deployable, it's usually the solar panel. I mean, there are other deployables, typically a radio antenna. But a radio antenna can be very, very thin and very, very simple. A solar panel is a major structure that often then needs to be articulatable. And one of the things I never understood, and I'll try to go through these slides fairly quickly because they're basically a parenthesis, is why the space world was so worried. I mean, we have millions of things on Earth that move, mechanisms. The convertible top on a Volkswagen or on a Mercedes or on any other. Nowadays, the style in convertible tops is not to make them out of canvas, it's to make them out of rigid metal. and then they have to, break into panels and fold up, and there's a million things that have to happen to them. And we do that all the time, and it's done in mass production, and it doesn't cost very much, and it works phenomenally. And even like airplanes, we have landing gear, and every flight, all three legs of the landing gear have to not just fold up, but tuck into the aeroshell and then get covered by little doors. And then you better believe we want them to come out, before we're going to land on the runway. And they mostly do. And, but when you go to space, there's this tremendous allergy to anything that has to move. And, I tried to go through in these stories why we work so hard to not have deployable solar panels. And the basic answer is that, the launch environment, I'm always blaming everything on transportation, is very harsh. And therefore, the thing needs to be bolted down very, very solidly. And in the case of at least one failure that I worked on, that was Galileo, one of the many satellites called Galileo. It didn't deploy in the end because of a lack of lubrication that caused vacuum welding. So, vacuum welding being in a vacuum, two pieces of similar material, identical material, that are pressed together the way we have to screw things together to keep them from vibrating before the launch, is going to eventually, the crystal structure is going to merge, and you're going to make it into basically one piece of metal, and you're never going to move it at that point. That happened to Galileo because of the Challenger failure, which caused it to be shipped back to California, put in nitrogen storage for, I think, a couple of years, and then shipped back. A lot of vibration that rubbed off the lubrication, a lot of time clamped together, and then it spent a lot of time in space before it got to the point where the antenna was supposed to deploy, and it didn't. So there are examples. That's an example of one that didn't work on slide 17. There's also examples of satellites that did a tremendous number of deployables and worked fine, and that would be Freya, another Swedish satellite that I worked on. And Freya I used as an example in the thermal of how to control thermal because it had these big fixed solar panels pointing at the sun. It was in a polar orbit because the Swedes are basically near the poles, and they were doing polar research anyway, and part of the instrumentation, and auroral research type thing. And so there were seasons of the year when the plane of the orbit was perpendicular to the line to the sun. And when that happened, it was illuminated nearly 24 hours a day, and the satellite would tend to overheat. And our solution for that is really what this illustration was about, tilting the satellite slightly 30 degrees away from the straight to the sun pointing that it was built to have, that decreased the solar flux on the panels by the cosine of 30 degrees, and that pretty much solved the problem. So, moving on to slide 18, solar panels aren't the only deployable, of course. There's fairings that have to open and then drop off. This famous canonical separation mechanism called the Marmon ring, which is basically an attachment ring. You put one ring on the satellite and one ring on the launch vehicle, and they're made convex, like you see in that picture on slide 18. And the way you hold those two, kind of extruded cylinders to each other is with a belt that wraps a V-shaped belt, that wraps around them. And then when that belt is severed by some sort of a pyrotechnic, it pulls away, and the two pieces are really free. They're not really attached to each other. They're just touching each other. And the interesting thing about that is you have this belt, and you can cut it in two different places. So if either one of the cutters fails, they're two independent cutters. So it's a redundant system for separating the satellite from the rocket, and yet when it's attached, it's totally attached. So it's a very nice system, and it's gotten a lot of use. It's not particularly easy to apply to a very small attachment like a CubeSat. But we also have to open doors. Quite often instruments want covers on them. I always try to discourage customers from using those doors because they can very easily get stuck, like a door on a telescope with a hinge. Seems like a simple thing, But if it gets distorted through vibration, if it gets distorted through thermal, it's not going to open. And so what I usually recommend is remove before flight. Put a cover on it to keep dust off of it and just live with it. Better that it might get a little bit dirty, getting through the launch and the deployment on orbit, than that it doesn't work at all. Of course, rocket stages themselves have to separate, and there's really quite a bit of engineering that goes into that. Solar panels and booms, like a gravity gradient boom, some antennas, and, like our attitude control system, drag devices, and other radar reflectors, things like that. So really, there's a pretty long list of things that want to deploy. One of my antis of gravity gradient is you have to deploy something, and that's not easy. And so, like, everybody so interested in gravity gradient because it's passive, but how passive is it? And this is another reason it's not so passive. You've got to get this major deployable out there. Okay, so how do we actuate things? Everyone immediately goes to the pyrotechnic bolts, which, get called explosive bolts. It's not a name that the manufacturer likes very much, which are bolts that have been partially severed already and have a pyrotechnic charge inside of them. They have a couple of flaws. One of them flaws is that it's a one-time. So when you test it, you throw it away, and then whatever one you fly has never been tested. Then another problem with them is, even though they're not supposed to be explosive, they can explode. And I've done some tests where you're not in the same room with it, and you want to be separated by like a concrete wall. And in fact, we found pieces of the bolt in the concrete wall. So, it's not supposed to happen, but it can happen. And they do take a lot of current. It's 5 volts times an amp or something to fire the explosive charge. And if you don't have that much battery power, that can be a problem. So then these other ideas, using wires that melt. Hot wax, I just want to mention it because it's very useful. It isn't melting wax, which would be like a melting wire where you seal something with wax and then melt it. These are cylinders with wax in them. And when you heat them, by turning on a heater, the wax melts and then it evaporates. And that creates a gas that's trying to expand against the cylinder, and it pushes the cylinder out. The advantage to that is you can let it cool and then heat it again. And sometimes things that are stuck, if you keep pushing on them, eventually they will break free. So these other things are fairly obvious. The one that's not so obvious is Doral, and there's many other, these are plastics that outgas 100% in space. So in that sense, maybe they're not the best actor, but they also try to develop them so that they're not going to recondense on optics and solar panels and things. That's a big problem with outgassing, is that you don't care that it outgasses other than it weakens the material, but you care if you have a cold surface like the lens of a telescope that's pointing away from the sun. Those molecules will find their way to the cold sinks and condense on it. And, it's a funny thing about satellites. You think they're in space, so they'd be super clean, but what really happens, it's a little bit like what they say in building a planet. You put, even molecules or small particles, dust, into space around your satellite. Enough of it will be charged and the satellite will be charged. You'll find that it all sticks to the satellite. It's just like on Earth. There's dust in your house. Where does it all go? It sticks to, your furniture, and it sticks to your windowsills, and it sticks to everything. There's van der Waals forces. They didn't mention in the film, but van der Waals forces count. The fact that generating surface area requires energy. I love that. It's one of those thermodynamic concepts. But why does it take energy to cut things? In the end, it isn't just, you can have an infinitely sharp knife. It's still going to take energy to cut something in half. And part of the reason for that, it takes energy to break water. This was the first problem I worked on at JPL. How do you make small droplets? Well, small droplets have more surface area than a big swimming pool filled with water. A swimming pool filled with water, 10 meters long and 3 meters wide, 30 by 10, 300 square meters. Take that water that's in that, and you can make it as deep as you want. You don't add to the surface area at all. Take that water and vaporize it into particles that are sub-millimeter and calculate how many of those particles, the surface area is increased by, 9, 12 orders of magnitude. And that creating surface area takes energy. So when you when you have small particles, their lower energy state is to agglomerate. And one of the things, and they will tend to agglomerate on things that are cold. So, because there's less thermal energy, so they can more comfortably sit on them without being upset by Brownian motion. So that's a real danger. So companies like DuPont have come up with materials that sublimate into gases that are gases, that don't sublimate into, tiny particles. Well, what's the use of those? The use of those is you want to create like a thermos bottle. So you've got a glass container or a metal container separated by a vacuum, because in space we got lots of vacuum, from the body of the spacecraft. That's great, except how do you hold it there? And how do you hold it there through the many G's of the launch with some sort of bolts, right? But then when you get in space, those bolts are thermal shorts. So you make those bolts out of dural, and when you get to space, they evaporate, and nothing's holding the thing there. Well, you got to have something. So you have very thin nylon filaments that are basically in tension and hold the thing in place. But the structure that you needed to get it into space through the launch load is gone. So those are also, that you can consider that sort of a deployment mechanism. And then I have this slide 20, which came from my 1995 book. And it's just pointing out that the idea that, we have all these deployable things on Earth and why don't we just use them in space is not so easy. And you can kind of read this for yourself. Things that deploy on Earth, I picked the antenna deployer that was in a lot of cars back, in that epoch. And, if you want to make that into a gravity gradient boom or you want to make that into a magnetometer boom, you've got to first think about that antennas on cars don't have a tip mass. They don't have a 5 kilogram weight out there, right? They're made out of plastic. They have negative ground. Because cars are negative ground, we can't have negative ground on a satellite because we can't have current loops, because that'll upset the ACS. So you have to get rid of that negative ground and replace it with a wire, which means you have to get rid of the metal outer shield of this thing, the metal chassis that it's built into, which is grounded to the motor. The motor itself is probably not going to work in a vacuum because it will overheat. And then you're going to have a lot of metal-to-metal contact in things like this that's going to vacuum weld. The 12 volts may not be a voltage that's on your satellite, and the current may be unappetizing to you. So, then you're going to decide, well, I've got to make all these changes, and you're going to tear it down and rebuild it. And by the time you do that, you do not have the original part. Well, I'm going to test it. Well, to get the reliability, when you think about it, General Motors sells a lot of cars with those antennas on them, and every day, there's millions of deployments. That's why the thing is so reliable. If it starts breaking in the field, they improve it. If you change it, you really don't know what you've got. So anyway, there's a lot of things that you need to do, and you're paying the engineers, what you're paying them to fiddle around with it. And if many times we decide, using this terrestrial mechanism is not worth it. I might as well just design it from scratch. They're not really made to be taken apart anyway. They're all pressed together and so on. It's a lot of work just to open it. And it's like, why am I going through this just to get a motor? I can open it and see how they do it and just copy that in materials that are compatible with space at a voltage that's compatible with a motor that will actually work. So, there's a great mythology over using terrestrial parts. And sometimes it works, but not all the time. And like everything in life, the key is knowing which is which, when to use and when not to use. But generally speaking, in mechanisms, I use them as a model for what I want to build, but I don't take them exactly as they came because it's very, very unusual that a terrestrial mechanism is going to suit your needs in space. So, will it really be the same part, slide 21, and how much is it going to cost to convert that thing into something you can actually use in space? So this leads me to a little bit of a philosophical discussion. What are your choices? And I think you guys are running into that on Sputnik. That, look, there's only 3 choices. You're either going to spend money for the flight qualified thing, you're going to use a terrestrial device and either modify it or qualify it by, testing it or convincing yourself that it's similar to something else, the things that Scott McDermott talked about, or you're going to make your own from scratch. And none of those options are perfect, which brings you to the trade-off. Do the pros and cons. Figure out whether there's one of them that is clearly going to be better for you. In terms of maybe one has something you can immediately say, this isn't going to work. Okay, Then this is, what they really cost. This was a long time ago I made this slide. But it's amazing how much 4 deployable solar panels can cost. Everybody's like, why does space cost so much? Because it's custom built. You can buy, a decent, console piano for $5,000. But if you want to pay someone to build a console piano, let's say space qualified, with all non-outgassing materials, that's going to last many, many years without tuning it, it's going to require like a lot of, I'm talking about an acoustic piano. It would be fairly useless in space, but just to pick an example, that's going to take years to redesign it. Pianos have, a 400-year history, and then there were many instruments that preceded them that were sort of like test beds, harpsichords, clavichords, et cetera, et cetera. All of a sudden, you want to do, in your company in a year, what has taken the artisans, 400 years to perfect, and have something that's going to reliably work in space for 7 years. Is going to use none of the materials we used on the ground. And many of the mechanisms, like when you press the key of a piano down, what causes it to come back up when you let go of it? Gravity. Oh, there's no gravity. Well, we have to use springs. It's going to be a lot of engineering. And a deployable solar panel, you're already seeing that with the AOCS. I have to get a hinge. Okay, what hinge? Well, there's a nice hinge, but that hinge is a little bit too radical, too violent, and that's liable to break off, so I need a viscously damped hinge. How do they viscously damp it? Well, maybe it has some sort of fluid inside of it. Is that fluid going to leak out under a vacuum? That's just a hinge. And we go through, and like one of the big problems with solar panels is, okay, we have some sort of spring. They're pretty big and they're pretty heavy, and when it gets to the end, what's going to stop it? Well, you can put a little block on the hinge, a little piece of metal that stops the hinge from opening. But think of the torque on that piece of metal. You could easily break it. Okay, well, let's put some wires out there, some little, piano wire. Well, then you've got to fold that wire up. It's the same problem as the gravity gradient boom. What if that wire gets snagged? Then the solar panel's not going to open. Then the mission is basically either compromised or over. And if one of the solar panels doesn't open and the other 3 do, how are you going to spin stabilize the satellite and point it at the sun? It's going to be a super difficult problem. So you've got 4 solar panels. It looks so simple. You see these satellites like the Swedish Astrid. It's not that simple. You really agonize over these things. There's a lot of engineering time and, and what materials you're going to make it out of, what exactly, are you going to use a hot wax actuator? Are you going to use a memory metal actuator? Are you going to use an explosive bolt actuator? What are the vibrations going to be? What is the thermal going to be? What's the possible outgassing going to be? You're going to go to program reviews. Your managers are going to look at it. You're going to prototype it. You're going to want to test it. And all those things take time and take, therefore, money. Not to mention that you're going to go to subcontractors and have the panels built probably because you don't have the facility to make, very efficient carbon composite structures. Okay, so it costs money, and that's one of the reasons that programs are allergic to deployable solar panels. And that's one of the reasons why I say to people, in a normal mission, if you're going to buy solar panels, you're going to end up buying gallium arsenide because surface area is expensive, much more expensive than solar panels. So you want to use the minimum of surface area with the maximum efficiency, and almost always the trade study goes to buy the most expensive, i.e. the most efficient solar panels you can. Okay, then this slide, number 25, it was originally made in Italian because I used it for teaching my students here, and I just left it because it's kind of cute. I think we tend to think of power systems, and I think we tend to think of power systems as pretty straightforward. They're in everything, right? You buy a razor, a Norelco razor like I use, and it's $29 at Amazon, and you recharge it every day for years and never even think about it. Just plug the charger in, a little yellow light starts flashing, and when it stops flashing, it's recharged. What's so hard about that, right? Well, one of the things that's hard about that is that solar panels are not a wall plug. Solar panels put out a lot of voltage, depending, right? They put out a lot of voltage if they're pointed normally to the sun and if they're cold. So they might be putting out 50 volts. And then if they're not cold and they're not pointing exactly at the sun, like they've been in the sun for a while, they might be down to 20 volts. So you could have a 2 or 3 to 1 or 5 to 1 ratio of voltage. Solar panels, depending on how hot they are and how much sun they're getting, will put out their maximum power at different voltages, how much you load them. If you short circuit them, the voltage drops to zero, even though theoretically, and the current does not go to infinity. So you don't get much. And if you open circuit them, yeah, you get a maximum voltage, 50 volts. Wow. But no current. So what's the right impedance to put across the solar panel? That's a function of a lot of variables. So you basically need a computer that knows what temperature the solar panels are, what angle they have relative to the sun, therefore how much I want to load them. And then somehow you have to have the same thing going on with your batteries that you want to charge. Lithium-ion batteries want different charging voltages and currents depending on their state of charge. It's different when they're 90% or when they're 10%. When they're 10%, they're very hungry. They will tend to ingest a lot of current, and that can be too much current, and you can overheat them and damage them, or that was the reason that they would use to catch fire. So you've got this strange matching problem between two different, the source and the sink, which are both variable. And so you have a fairly complicated algorithm. Nowadays, you buy rechargeable batteries, lithium-ion batteries. They quite often come with a charging circuit in them, which just says, look, guy, give me 12 volts and we'll take care of the rest. That happened because people were screwing up the charging algorithms, and that was causing a lot of the fires. So now they've, kind of taken the hard part out of the equation and just said, put 6 volts on this battery or put 3 volts on this, and they Zener diet it down, and then they do the regulation according to the battery temperature and all these other things that are going on, all within the battery itself. But quite often in space, it's DIY. And then you have, then you have the rest of the power system. It isn't enough to just have solar panels and batteries that you charge up. You also have to have a way to get that power, electric power, to all the places. So you have the wires and the cables, the Cavi and Feedly, which are like your veins and arteries, right? You have to have the arteries carrying the electrons out and the veins carrying the electrons back, because you can't use like a negative return through the body because you'll have current loops. So you do have veins and arteries, and you do have something like a heart that pumps the electrons out, and we would call that heart the, I called it the recharging mechanism. But in a way, it's DC to DC converters also, because you have to have the right blood pressure. For every part of the body is set up to absorb a certain blood pressure. And then you have to have, obviously, in a body, the way you store energy is in your cells, in your muscles, in organs, and also in the blood itself. I mean, there is an analogy there. And when you think about it, a great part of the resources of your body are involved in respiration and circulation of blood. And all that is the energy. That's the thermodynamic mechanism of your body. So I encourage people to not take it for granted. And I really push the Equisat people. The number one killer of CubeSats is failures of the power system. And it's as big as all the other failure mechanisms put together. So the idea that this is simple is a pretty naive idea. It's one of the most complicated things on the satellite. And unfortunately, nowadays, most electrical engineers are digital engineers. There's very few people who work in the analog realm, and this is a mostly analog problem. So you also have trouble finding people who have this experience. Okay, so there's a bunch of other slides here about oddball topics. One of the things to remember is many satellites are not stabilized, and so what matters is not how many solar panels they have, but what is the projected area of those solar panels on the sun. That's fairly obvious. It's reduced into 2 dimensions. It's 2r. The total projected area. It's not pi times 2r, because the sun is coming from one point, and the solar panels that are not pointing at the sun, or the part of the solar panel that's not pointing at the sun, is not getting a full dose of sun. So, you can have a sphere, which is 4 pi r squared, but the actual irradiated surface area effectively is pi r squared. So just the surface of the circle that I showed in the orange dot. I think that's fairly obvious, right? It's just the projected area is really what counts. A little bit more subtle is slide number 27. I worked on a project that built a parallelepiped satellite like this. And the idea was, well, the top and the bottom barely see the sun because it was sun pointing on the sides. Therefore, let's not put solar panels there. It's a lot of work, et cetera, et cetera, et cetera. And I was the guy who said, wait a minute. First of all, I didn't get started on it because I was so smart. I got started on it because I'm so nervous. And I thought, if you leave a panel without a solar panel, that will end up being the surface that's pointing at the sun, and then you're going to be kicking yourself. If I had a solar panel on that surface, I would be making power now, and as it is, I don't have enough power to rotate my satellite to point at the sun. Many satellites have died that way. So what I say to people is, even if you don't have very much of that surface area available, take it. And at least if you have to wait 2 weeks, sooner or later you will charge the batteries. That's what I say to people. Put solar panels every place you can, because you never know what the attitude is going to turn out to be like, or whether something's going to be blocking you, or whether you're going to have to charge from Earth albedo, or who knows what crazy thing is going to happen in space. The one thing you have in orbit is time. You can sit there and integrate up those batteries for a month if you have to, but not if you're charging at zero. It turned out to have a second advantage, which is maximizing the minimum. When you engineer things, you always have to engineer for the worst case. What's the worst case? The worst case is the middle of the winter and the middle of the summer as seen by the satellite, i.e. when the sun is not perpendicular to the surface. That's when those big solar panels are going to be making the least power. So you have to design the whole satellite to live at that power level, which is about 90%, let's say, of the maximum. Whereas if I put those cheapy solar panels on the ceiling and the floor, if I can, they create more power just when the other solar panels are creating the least power because of the cosine loss. And it just so happens, because of the dimension of the satellite, we were able to maintain virtually 100% power. So, it's not a big thing. It's not like, wow, this made the whole mission possible. But we don't always get paid for that as engineers. If you can make a 1% improvement, that's a 1% improvement. It's going to allow an instrument to be turned on that otherwise wouldn't have been turned on. It's like financial people. My wife used to manage, finances for big arts organizations, and they would have $100 million in the bank, doing something. They'd have $100 million of flux, that ticket sales and artist payments and rent and all that. If one day they happened to have $100 million in the checking account, they had a person who worked full-time for them who did nothing but invest that money from 5 p.m. to 8 a.m. when they would start cutting checks again. And, that's a pretty niche job, and you don't earn much interest on half a day of investing. If you think a few percent a year, that would be 1/100% per day, and you're investing for a half of a day, so it's, half of 1/100%, but half of 1/100% every night is a lot more than that person was earning. And the same thing can be said about you. The satellite program might be $500 million. If you can give it 1% more energy, that's 1% more mission, that's $5 million. That definitely paid your salary, like for your whole life. So, every so often, I'm not much of a detail person really, but every so often I like the subtlety, and one of the subtleties of finding a little waste, a little, dropping resistor that I can say, that dropping resistor is wasting 1/4 of a watt, duty cycle 100%. Can we get rid of it? Can we redesign the circuit so we don't need it? And that's very satisfying to me, to have been just a little smarter. And this was a case of being a little smarter and realizing that it doesn't matter how much solar capacity you have on a good day. It matters how much you have on a bad day. Okay, so, these next slide, 28, is trying to, this is just a review slide. The packing factor, how much actual germanium or silicon can you get on the paddle? It depends on a lot of factors. Wiring, they come in tiles, and those tiles have a certain dimension, and you can't cut them. And so if it's not an even integer packing, you're not going to be able to use the whole panel. It's just the paddle size has to do with all the various dimensions that are, of the satellite. whereas the the little tiles have to do with what the solar panel manufacturer makes. And of course, it's not perfectly pointed at the sun, and the temperatures are oddball all the time. And these are the things we went through on the very first day, just a review of that. And in terms of the battery design, the question really is, how many joules, how many watt hours do you need when you're in the shade, right? And then how efficiently can you actually use the battery power, meaning the battery's discharging is not 100% efficient. The DC to DC converters knock out a little bit. The wiring knocks out a little bit. How many cycles are you going to run those batteries through? Typically in a low Earth orbit satellite, 17 cycles a day. That's a lot of cycles if you're in orbit for 1,000 days, which we were on Equisat, 900 and something days. And your average battery that you buy at, Home Depot is going to advertise 500 cycles, like that you put in your rechargeable toothbrush. Well, maybe 1,000 cycles maximum. That'll last you 3 years if you use it every day. But in fact, that's not much for a satellite that's going to go through 17,000 cycles in less, in 3 years. So we fight that with depth of discharge. Excuse me. By using the batteries more lightly, they last longer, but that means you're going to need to double, triple, quadruple the mass of batteries so that instead of discharging them 60%, you're discharging them 15%. Then the battery capacity is going to drop anyway with time, so you really have to think, well, if I want to do a 3-year mission, how much capacity is going to be in these batteries? Okay, we can drive ourselves crazy with that because solar panels degrade on orbit too at about 3 to 7% a year. But the other thing that tempers it is, I'm very biased toward the present. And really 3 or 5 years into the mission, unless you're a geosynchronous ComSat, most of the instruments are not interesting anymore. They're going to be turned off because they will have done what the scientists wanted to do. I wouldn't drive myself totally crazy making sure I have 100% of power and 100% of battery capacity on the 1,000th day of the mission, because probably the interest in the mission is going to be really waning. And what's the worst case? You can't run 100% duty cycle, so shoot me. Because, okay, you'd say, well, isn't it nice to have that? Yeah, it's nice to have that. Who's going to pay the $10,000 or $20,000 a kilogram to fly solar panels that I really am not going to ever need? And what happens with missions is they go, what I call get out of the box. You got a 3U cube, and then when you throw in all the, margin that every one of the generals wants you to, and every one of the lieutenants, and every one of the lieutenant colonels, and every one of the colonels wants, you end up, with a big satellite. Okay, well, this is the big satellite we need in order to generate 100% of everything with 100% reliability, all space qualified parts, and now it's a 1,000 kilogram satellite, or now it's a 500 kilogram satellite. And then the customer is like, well, I don't have enough money to do a 500 kilogram satellite, so we're not going to fly it. That's a 0% reliability. The better is always the enemy, and I wouldn't back off saying always. It's always the enemy of good enough. And I've seen many good programs never fly because they got all hung up in, but we can't take this risk, and we can't do that risk, and we have to have this big of a solar panel because they degrade 7% per year. And, life is full of risks. I hate to sound like, Bolsonaro saying that everybody dies sometime. But you have to do the art of the doable is what I'm really talking about. So the end of this whole presentation, or nearly the end of the whole presentation, is a spreadsheet that I'll put in resources, which is a pretty simple spreadsheet. It goes system by system by system and says what's the duty cycle of each one. If you have a processor and it takes 1 watt and it's on 100% of the time, you need a watt in your power budget. If you have a radio and it's on 4% of the time and it takes 10 watts, you have 0.04 times 10 of a watt, in your, which would be 0.4 watts. In your steady state, how much do I need per day? Of power. You want an average number of power. What's the satellite consume on average? So then you're charging, let's say you come up with a number 10 watts, right? Then you're going to go through, okay, I need 10 watts all the time. I'm only in the sun 60% of the time. Therefore, I need to make more than 10 watts when I am in the sun so that I'll have 10 watts available when I'm not in the sun. So this spreadsheet does all those calculations. I don't want to go through it on this podcast because we're already up to 40 minutes, 44 minutes. So I'm going to do a quick separate podcast just to explain that spreadsheet. It's composed of a few different parts, and first you go through the power budget, and then you go through the charge-discharge cycle. It's handy. You can use it if you want to use it. It's not that useful for the satellite that we're currently building, but it's pretty much a generalized tool that, I use on generalized, satellite design problems. Okay, switching over to the slide 31. One day we're going to do better. And, this power thing, there's 3 apertures on the satellite. There's the power, there's the radio antenna, and there's, the optical aperture or the sensor aperture, whatever it is. And we really need to do more R&D on apertures. And unfortunately, we don't. We just throw money at it and build bigger and bigger deployables. But I think you do see a little bit of progress in flexible arrays, in inflatable structures, in large deployables, in how do you stabilize flexible. Yes, we're making progress. We're making progress about 1% as fast as if we took this problem, seriously. So, and my very last slide is try to get away from deployables by reducing power requirements, possibly getting a larger physical envelope, even if you have the same mass, which is, what the University of Colorado Snowy satellite did. It was a small satellite. It happened to have a big space. The space in between the main payload and the rocket was a big cylinder, and they took the whole thing just so they could cover an empty box with solar panels. At least it was static, and they didn't have to waste money and time designing a deployable. And then if you do have to design deployables, you want them to work at 1G and 1 atmosphere so you can test them over and over again, even upside down. If they're right side up, they're going to deploy too fast. That's good. If you can stop them, in 1G, it'll definitely stop them in 0G. If you can deploy them against the force of gravity, that means when there is no gravity to help them, they will still likely work. Okay, hope this was an interesting, excursion into the world of power. I will do a quick podcast, 10 minutes on how to use the spreadsheet. Other than that, we can move on to a new topic.